Hello everybody, welcome to this supplemental lecture for MME 2305, Material and Energy Balance. Today I'm going to talk about balancing equations. So in case you're wondering why we care about balancing equations, it just so turns out that several metallurgical processes that we care about involve chemical reactions. And to perform material balances on these processes, we need to understand the specifics of the chemical reaction involved. If we take a look at copper refining, we know that copper, like all metals, is found in the crust of the earth. It is generally found bound with other elements. So we have some common ores, and so this is some, but definitely not all, of copper-containing ores that are mined out of the earth. One of them is chalcopyrite, which is copper bound with iron and sulfur. The other one is chalcocite, which is copper and sulfur. We also have oxide ores, and one of them being cuprite, which is copper bound with oxygen. So when we're refining these ores, we generally feed them to a blast furnace. We want to do something to these ores to purify the material so we can get pure copper in this case. So here we would charge to a blast furnace chalcopyrite, some silicon dioxide, and some oxygen. If you notice, the output to this is not pure copper. It is, if hopefully you're familiar with, the chemical or the material chalcocite. So this chalcocite would then go to another blast furnace for further refining. The purpose of this blast furnace would be to remove the iron from the chalcopyrite. That iron then bonds with the silica, so you get this iron silicate, which would come off as slag. And typically you skim that off of the top of a melt. You also get SO2, which is can be refined and used to produce sulfuric acid. It was once said that the copper refining companies were making more money off of the production of sulfuric acid, which otherwise would be a pollutant, than they were of actually copper production. I don't know if that's still true today. But before we can do any material balance involving what we know about this blast furnace, we first need to understand the specifics of the chemical equation. So if we look at this unbalanced chemical equation, you can kind of look at it in terms of input and output. In chemistry, I think we refer it to as reactants and products. And hopefully those are familiar terms to you. So I want to talk now specifically about how do we go about balancing an equation. And in chemistry, when I was young, I remember, you just kind of looked at it, you played around with the numbers a little bit. Here, since we're engineers, we want to do things a bit systematic. And if you've seen this type of process before, this will be a review. And if you haven't, it's always good to learn something new. And it also never hurts to do a little bit of review. So the way we go about balancing equations in this class anyway, is we assign arbitrary coefficients to each of our chemicals in our chemical equation here. So I'm going to assign X, Y, Z, and I'm also going to assign A, B, C on our products. I tend to try to use arbitrary coefficients that don't match elements. That's hard to do oftentimes. C potentially could get confused with carbon, but we'll try to keep everything straight today. Okay, so the next step is I want to set up a series of equations for each one of my elements involved in this chemical reaction. So I look here, I have copper. I also have some iron. I also have some sulfur. I also have some silicon and some oxygen. And I have oxygen in two places there. Let me scoot the sulfur and silicon over. Sulfur, silicon, and oxygen. Okay, and so now I want to set up a series of equations would be the next step in balancing my equation. So for copper, I have X. I don't see copper anywhere else on my product side or my input side. I do see copper here, and I see two of them. So X equals 2A, because I have Cu2. I don't see copper anywhere else here. So the next element in my chain here is iron. So iron, there's only one iron here in my chalcopyrite. And so it is just simply X. And where else do I see iron? Well, I don't see it till on the other side here with B. So X equals B. The next element in our reaction here is sulfur, and I see two sulfurs here, so 2X. And I see copper here, so equals, I'm sorry, I see sulfur here next to my copper, equals A. And do I see sulfur anywhere else? Oh, yes, I do. 2X equals A plus C. The next element in our chemical equation here is silicon, and so that's Y. And do I see silicon anywhere else here? No, I do not. I don't see it till we have our iron silicate, and we see it here only once, so it equals to B. And the final element we have is oxygen, and we see it twice. We see it with our SiO2 and also our O2 by itself here. So 2Y plus 2Z, and I see it two places here, equals 3B plus 2C. And I'm running out of room there, so let me restate that. Two Y plus 2Z equals 3B plus 2C. Okay, and so now what's the next step? Well, we talked about assuming bases when we did our basic mass balances. So here we're going to assume a sort of basis. We're going to assume X equals 1. Okay, and you could assume any number, any arbitrary number, okay, but I'm going to assume X equals 1. So this tells us now X equals 2A, okay, sorry, 1 equals 2A, so A equals 2 1/2. So we're beginning to solve for our equations. X equals 1, right? So 1 is equal to B, so that means B equals 1. So then we come over here, 2X plus A equals C. Well, A equals 1 again, so 2 equals A. We already know what A is, 1/2 plus C. So now we know that C equals 1 1/2. And we can be consistent. We can say B equals 1. Here we have Y equals to B, so now we know Y equals 1 because we know that B is equal to 1. And so for my kind of messy equation here, we can solve that now. So we know that Y equals 1, so 2 plus 2Z. We know that B is equal to 1, equals 3. And we know that C is equal to 1/2, so that means this is 3. So 2 times 1 1/2 is 3. Okay, so then we can rearrange this and solve for Z. So Z by my math is equal to 2. Okay, so now we're one step closer to solving our equation. So we know X is 1, so we can say CUFES2, okay, because we know X is 1. We know what Y is, okay. And where did I find Y? Y equals 1 plus SiO2. And we know that Z is 2. And that goes to 1/2 because A is equal to 1/2. B is equal to 1. And C is equal to 1 1/2. Okay, so we're not quite done. In material energy balance, we generally like our equations to be balanced with whole numbers. So what would make this a whole number? 2. Would multiplying this by 2 also make it a whole number? Yes, it would make it 3. So we multiply the entire equation or both sides of the equation by 2 to get a whole number again. So we can write our balanced equation now is 2 CUFES FeS2 plus 2SiO2 plus 4O2 goes to Cu2S plus 2FeSiO2 plus 3SO2. So here is the systematic way that we do or we apply to balance equations. There are some interesting, I guess, relationships that we can derive here. So if I say I give you, 100 kilograms of chalcopyrite, based on this chemical reaction, how many pounds of copper sulfate would you get? And so if I give you 100, 2A, so you'd get twice the amount of copper. So it helps you with your mass balances. It's also a very systematic way to balance an equation. If you have any questions, you can always email me at drobertson@utep.edu. And thank you very much for your time.
Oh my. It's the end of the lecture. If you have any questions, you can email me at drobertson@utep.edu.